Hello everyone, how's it going? My name is Dan the Tutor. Today we are going to talk about the magnetic field in a solenoid, which first we should talk about what is a solenoid. So a solenoid is just like a cylinder, like a can of tomato soup if you want to think of it like that. And if you were to take your can of tomato soup and you were to wrap a wire around it, like this, all the way around, all the way up and down the can of soup, now you have a solenoid. And what's essentially going on here is that this would be part of like, a bigger circuit or something. So like the wire keeps going and it's, connected something like there. But what I really want you to focus on is just the can of tomato soup right now. So you take your can of tomato soup, you wrap a wire around it, and then you put a current through it. We'll say some current I. It doesn't matter what I is. And all of a sudden you've just generated a magnetic field. Now let's say the direction of this wire, this current in the wire points, I don't know what direction you would say. You can say it points to the right here, but again, this is like a front view. If you think of it from like a top-down view perspective, you've got now it's just like a circle with the current going around it like that, right? And so actually I can find the direction of my magnetic field pretty easily. And I'll show you both ways. I'll show you from the top-down view and I'll show you from the front view. Now first I'll show you from the top-down view because I think that's easier. I'm going to choose this point right here at the bottom. At that point right there, it looks like the current I points to the right, like at that point only. And if you remember my right-hand rule for current in a wire, I said that I use the curl finger method where your thumb points in the direction of your current, so to the right. And then if I curl my fingers, that's the direction everywhere around it. Now, I want to find the magnetic field specifically in the middle right there. And so that point I just drew, we'll call it point P, is above my thumb, right? Because my thumb is the blue wire, point P is above. If I consider curling my fingers above my wire, above my thumb, it looks like my fingers are curling back into me, towards me. So that means the magnetic field at that point is going to point out of the page, which is that symbol there, circle with the dot in the middle. That's out of the page. And so if I think of the same thing from my front view, if I choose this point right here, this is the front of the cylinder, the front of my can of tomato soup. I'm going to still point my thumb to the right. And now, if you think of it, this is kind of confusing, but your point P over here is somewhere behind me. And the reason why is because this is the front of my can of tomato soup. The center of the tomato soup is obviously behind the blue dot I drew. Or maybe it's not obvious to you, but I'll tell you it's definitely behind the blue dot in a 3D space sort of sense. And since it's behind me, my thumb points to the right. I'm considering my fingers kind of like behind my thumb, behind it. And it looks like my fingers are curling up at that point. And that's exactly the direction of the magnetic field. The magnetic field points up in the front view, points out of the page in the top-down view. And in case you're curious, if I look outside of my solenoid, it's going to wrap around like that for the direction. So this is the way the direction of my magnetic field points inside the solenoid. That's direction only. Of course, I also want to find the magnitude of my magnetic field. So if you remember the equation, B equals mu naught I over 2 pi r, this is the equation for current in a straight wire. Obviously, this is not a straight wire because it's constantly bending around my solenoid. So then, in other words, this equation won't work. We need a new one. Now, I'm going to give you the equation. In case you're wondering where it comes from Ampere's law. And I'm not going to explain Ampere's law in this video. I'm just telling you if you want to derive it, that's how you do it. But the equation you end up with is mu naught times n times I over L, where n is the number of loops in your solenoid. In other words, how many times you wrapped your wire around your can of tomato soup. I don't know why it has to be tomato soup. I guess it doesn't have to be. It can be chicken noodle as well if you prefer. And then L is the length of your solenoid, and that is this, whatever height this is, length L. Now, the other way you can see this equation, by the way, sometimes you'll see it written like this, mu naught lowercase n times I. And if you ever see this, That's because lowercase n is equal to capital N over L. It's equal to turns over length L, which is in meters. And the reason why you would use this equation instead of the top one is if they ever say the phrase turns per meter. That's when you would use the bottom equation. So let's look at two quick examples here. Let's say I have a solenoid that looks like it's on its side. I'm going to wrap my wires around it like this, and the current's going to point that way, if you think of it. And I'll say the value of the current I is 50 milliamps. The length of my solenoid we'll say is 2 meters. And I know I drew like however many wires, but I'm going to tell you that the number of turns is 100 turns in this solenoid. So I want the magnitude and the direction of my magnetic field. So first, if I want to find the direction, I need to consider my thumb being the actual current, which looking at this point looks like the current points up everywhere along here. And then I have to curl my fingers at the point I'm looking at. Now the point I'm looking at is like inside of my solenoid, so it's behind my thumb, which means if I consider the point behind my thumb, my fingers are curling to the left. If you can see on my screen, if you mimic my hand motion, I know it's reversed because like you're looking at me, but this is pointing to the left. And so the magnetic field is going to point left. Now if I want to find the magnitude of my magnetic field, I just use the equation mu naught N times I over L. The reason why I'm using this one is because it didn't tell me turns per meter. So that means mu naught is a constant, 1.26 times 10 to the minus 6. N is 100 turns. I, the current, is 50 milliamps. So you need to divide that by 1,000 first to get that. And then divide it by the length, which was 2 meters. If I plug this in a calculator, then I will get a magnetic field of 3.15 times 10 to the minus 6th. And the units for magnetic field are T Tesla, named after Nikola Tesla, not the car company. So that's it for that example. And now for the last example. This time I'm going to tell you my solenoid. We're looking at it from a top-down view. This is the top view. And my wire is going to wrap around this way, let's say clockwise. So that's my wire wrapping around. I is 1.2 amps. I'm going to tell you that this solenoid has a length. I know you can't see it, but it's like going down. The length is going to be 40 centimeters. And this wire is going to have 75 turns per meter. So this is the case where I would use B equals mu naught lowercase n times I. So this is really easy. 1.26 times 10 to the minus 6th times lowercase n, 75, times I, which is 1.2. And if I plug this in my calculator, I will get 1.134 times 10 to the minus 4th. Still, the units are Tesla. That's the magnetic field. You may be wondering, Dan, why didn't we use the 40 centimeters? That's because I have a part 2 to this question. My part 2 is how many turns are in the wire. And to figure out the number of turns, you need to remember that n, lowercase n, is equal to turns per meter, uppercase N over L. So lowercase n we said was 75, equals n, which is what we're solving for, divided by the length, which was 40 centimeters. Of course, I need to convert that to 0.40 meters. So multiply 0.40 by both sides. 75 times 0.40 equals n. 75 times 0.4 is 30. So there are 30 turns in this solenoid. And the last question I want to ask, still for the solenoid, is what's the direction of my magnetic field? So the nice thing is you can choose any point on this solenoid. You can choose above, you can choose to the right, you can choose below, or you can choose to the left. Since it doesn't matter, I'll just choose this point at the top here. At that point, my current points to the right, so my thumb points to the right. The point I'm looking at is towards the center, so below my thumb. I need to consider my fingers curling below my thumb. It's going to require some serious gymnastics here to do this, but if I point my thumb to the right, fingers are curling into the page, it looks like, and that's the direction of my magnetic field into the page, which is the symbol with the circle with the X through it, that's the direction of my magnetic field. And that's going to do it for today's lesson on magnetic fields in a solenoid. Thank you all for watching. I hope you have a great rest of your day. Take care, and bye-bye.